let's use the second partials test to determine the relative extremum of functions and classify whether or not they're maxima, minima, or saddle points. So remember, to do that, we're going to need to get we're going to get all three mixed derivatives. The second, the partial with respect to x, second partial with respect to y, and the mixed partial xy. So we need to find the critical points and then use this second partials test. So the first thing we want to do is find the first partial derivative with respect to x. So 2x plus 8. And the first partial with respect to y is 2y minus 12. So if we go back and realize that anywhere where x is -4 and anywhere where y is equal to 6, so we have a -4, positive 6, and if we go plug that in, we end up with 16 plus 36 is 52, minus 32 is 20, minus 72 is -52, -55. All right. Is that right? Minus 16, minus 32. Give me just a second here. So that should be 16, 36, 50. Yeah, so -55. I apologize. All right. So then we need to find our mixed partials. Or rather, just our second partials. It's 2. Our second partial with respect to y is also 2. Our mixed partial is 0. So that tells me that d is 2 times 2 minus 0 squared, which is 4. So what I have is a second partial that's positive and a d that's positive. So when I check my chart, that tells me that this must be a minimum. So then I continue on. I say, all right, g of xy is this piece, so I need to find my first derivative. Or first partial, rather. 2x minus 1. First partial with respect to y is -2y minus 1. So that tells me that the point 1/2, -1/2, and if I plug that in, I get 1/4 minus 1/4 minus 1/2 plus 1/2. So that tells me 1/2, -1/2, 0 is the point. Then if I take the second partial, then I get 2, -2, and a mixed partial of 0. So d is 2, -2 minus 0 squared, which is -4, which is less than 0. So I have a positive value here. Actually, I don't even need to worry about this. I have a d that's less than 0. So since I have a d that's less than 0, I know I have a saddle point. And again, that makes sense because that's going to be a hyperbolic paraboloid. So let's keep on going. So we need to find the first partial here. Okay, so in this particular case, we need to find where these are equal to 0. Well, what I see is that if x is 0, y can be anything. And if y is 0, x can be anything. Right? If x is 0, it doesn't matter what I plug in for y. And that would be true here. If I plug in 0 for x, it doesn't matter what I plug in for y. And if I plug in 0 for y, it doesn't matter what I plug in for x on both of those. So my critical points are any points along the x-axis, any points along the y-axis. It's not the whole x-y axis. You just ride the rails, because anytime you're on the rails, one or the other is 0. So that also includes the origin. And anytime that those are along the rails, the output of the function is 0. So you could parameterize that as x 0, 0 or 0, y 0. Anything of that sort of point. All right, so let's get the second partials. Okay, so if I plug, as long as at least one of these things are 0, all three of those are 0. Well, that's an inconclusive piece, right? Well, junk, we're just done. There's no way around it. But that's not true, obviously, right? There's got to be some way to think about this. So let's go and let's think about to the original problem. Let's look at this thing. Well, let's think about it. When if I plug in something for x, anything for x that's not 0, then that's going to go to the 4th power, so it's going to be positive. If I plug in anything for y, no matter whatever I plug in, it comes out positive. So anything that's not along these axes where both of these are not 0, doesn't matter what they are, as long as they're both not 0, that's positive and that's positive, but when it multiplies by 2, it's negative. So what I'm hearing is along the rails, everything is 0, but everywhere else, it's negative. So that tells me that no matter what, these points are maxima. So we just sometimes you have to be more clever than just plugging into the second partials test. But finally, we have this piece. So if I get my partial, I get my partial, okay, I have two expressions here. And remember, to find the critical point, I have to set them equal to 0. So I need to say, okay, well, 2x minus y minus 3 is equal to 0. That tells me that y is equal to 2x minus 3. So if I have negative 2y minus x minus 1 is 0, then negative 2x minus 3 minus x minus 1 is 0. Negative 4x plus 6 minus x minus 1 is 0. Negative 5x plus 5 is equal to 0. X is 1. So if x is 1, that tells me y is negative 1. So that tells me my critical point is 1, negative 1. So 1 plus 1 minus 1, so that's 2, minus, so that's 1, minus 3 is negative 2, plus 1 is negative 1. That's my critical point. And now I need to use my second partials to determine what type of critical point it is. So second partial is 2. Second partial with respect to y is negative 2. I could get my mixed partial, but those two are already opposite signs. So if those are already opposite signs, that tells me that D is going to be negative. So since D is less than 0, that tells me I have a saddle point. And you could have guessed that because this little xy might throw you off, but otherwise the general behavior of this is pretty much the general behavior of this. What that xy does is it basically says I have the same thing, but it's rotated a little bit. But if it's rotated, it's still the same type of behavior. So it's still going to have a saddle point at 1, negative 1, negative 1.